I'm Jason Peters, and here with Blue Earth Labs. Okay, so there's not a lot of introduction to distribution systems that I need to do with this crowd, but it's a good idea to take a few moments and talk about microbes, because microbes are a very significant part of our world. So when I say microbes are everywhere in your system, they really are, even though you didn't maybe know it or you didn't observe it. And we'll explore that a little bit. But this slide right here just gives you a flavor for where you might find microbiological activity in your system. The filters, pipe walls, any storage systems, and so forth. And so this is really where we want to focus our presentation. So I'll talk a little bit about microbiology, and then we'll come right back to this, and we'll talk about the impacts that the microbiology has on the operation of your system. Our goal here is to help you understand how to operate your system better and cleaner, and so that you can avoid a lot of the problems that microbes present in your system. And you'll find that they underlie almost everything that you do in the water industry, just like they underlie almost everything that happens in the world around us. It turns out that for every human cell that you have in your body, you have about 20 microbes. So for every human cell, there's 20 microbes. But the microbes are much smaller than your human cells. And so that amounts to only about a quarter pound, right? So you've got about a quarter pound of bacteria and other microbes in and on your body, right? So that's a lot if you think about it. 200 trillion microbes that you've been walking around with all of your life that you probably didn't even know were there. And there's about 1,000 different species of microbes that are in your own body as well. And if you look at just a square inch of skin, you can see about well, you can't see it, but there are about 600 on average, 600,000 microbes in a square inch of your skin. So when you're looking at your distribution system and you think, oh, well, my distribution system's clean, it doesn't feel slimy, there's no overt problems here, I don't see any biofilm or any attached bacteria. In reality, it's all there, you just don't know it. In fact, it turns out when a baby is born, they have a sterile mouth and intestines. But at their first feeding, they receive all the microbes that they need for the rest of their lives, right? And so that actually is what processes the food, helps process the food so that our bodies can absorb the nutrients. So we need them. And a teaspoon of soil that surrounds your distribution system has on average 10 million microbes in just a teaspoon of soil, to give you an idea of what is there and why it's an issue when we have low pressure events and we get water sucked back into our distribution system. It allows our distribution system to get seeded with microbes. So here's an example of the size that you might be wondering how it is that you can get 600,000 microbes on a square inch of skin. Well, this is the cross section of a human hair. To give you a flavor, that's about a cluster of about 100 E. coli bacteria. And so it's pretty easy to see that just looking at the number of hairs that you may have on your hand or your arm, that you can get quite a few bacteria on that surface and not really even notice. And bacteria, microbes in general, we're going to talk mostly about bacteria today. And bacteria will form what's called a biofilm when they're stressed. If you have bacteria and you apply a chlorine residual, there's a defensive mechanism which will secrete some sticky substance, and it will allow it to stick to a wall, and it will allow it to stick to each other. It will allow it to protect itself from disinfectants and so forth. And so we see bacteria doing this. In fact, bacteria, they can be found in space, they can be found in the deepest parts of the ocean, they can be found a half mile or more underground. If you take all the bacteria on the planet, the weight of it is more than the UK. So it's prevalent. The most common organic chemical that exists on the planet is cellulose, and that's what forms that's what bacteria actually secretes when it secretes a sticky substance, and it's also what makes the cell wall. And so this is kind of my primer, if you will, on microbiology, let's just stop and take a moment and rethink how we think about these processes that happen in our water system. and recognize that microbiology plays a large role in it, more so than we attributed before. And so that's why I like this Mark Twain saying, where it ain't what you don't know that gets you into trouble, it's what you know for sure that just ain't so. There's a joke, it's one of my favorite jokes when it comes to science, and it goes like this. So you have this police officer is walking down the street, and he sees this guy. He's under a street lamp, and he's looking around, and he's looking, and the police officer is concerned, he wants to help him out. So he's like, well, what did you lose? He's like, I'm looking for my keys. And so the police officer gets down, he's helping him out, they're looking for 15, 20 minutes. He can't find them. It's just a street lamp, so there's not that much area. So he asks him again, are you sure you dropped your keys here? He's like, no, I dropped them over there across the street, but here's where the light is, right? And that's exactly how science works. In science, we have certain tools that will illuminate a certain area. We have things that, tests that we can run, and ways of viewing things and understanding things. And for the longest time, it was inorganic chemistry, right? All the different atoms on the periodic table, how they interact. That's inorganic chemistry. And the rules that define how they work together are fairly simple. Well, organic chemistry, by the way, there's only about 1.7 million different compounds for inorganic chemistry. Organic compounds, there's about 10 plus million compounds, but they're all made out of carbon, hydrogen, oxygen, nitrogen. Just a few different elements. But they're big, and their shape matters. They're complex to analyze, and they're expensive to analyze. And so the light that's shed on those compounds is relatively small. So our understanding of how they work within our water system is relatively small. And the same thing applies for the 1 billion different kinds of bacteria that's estimated to be on the planet. We have a very limited understanding of how they work and what they do and how they interact with the environment. What we can observe is the after effects of what they've done. Like, for example, tuberculation. If you have iron and manganese in your pipe, you're familiar with these tubercles. Well, that's a phenomenon of bacteria. Okay, and so you might ask yourself, well, I come up clean in all my tests. I don't have bacteria in my water. I'm not getting any positives on my total coliforms or anything like that. My water system's good, and that's good. From a health perspective, what you care about is the bacteria that's in the water column. And chlorine or chloramines, they do a pretty good job of taking care of the health problems that are associated with the water column. But only 1% of the bacteria in your system exists in the water column. The other 99% are stuck to the wall. They're protecting themselves. They're essentially a little factory working to provide for themselves, and as a result, they have byproducts that they shoot off as well as their own children. So we end up seeing the development of bacteria. They stick to a wall, they start to secrete sticky material, and then they grow up and they continue to build until finally they're so big they need to send off some of the bacteria to move off to a different location. And so this is the kind of operation here going on in your system that causes some problems. And some of those problems are listed here. When you have bacteria in your system, it's not necessarily a health problem, not directly, but it's often an operational problem. It'll often cause problems in operation that you wouldn't normally attribute to bacteria, whether it be red water or main breaks or arsenic levels or leaks or corrosion. These are things that are not directly, we don't commonly think of bacteria, but bacteria is at the underlying root of the problem. All right, so we can't really talk about bacteria in water without discussing a little bit about pathogens, the things that actually make you sick, as well as some of the regulations to protect you from those. So the good news is that the pathogens that find themselves into water systems are secondary pathogens, right? It's not like anthrax or something like that that's going to make everybody sick. Instead, it's just going to make folks sick that have a weak immune system. So, which is great for all of us because we're here, we're fairly strong. But what about the folks that are immune compromised in a hospital or a healthcare facility, or children, babies, things like that? So we're here to concern ourselves with the entire population. All right. Here's a couple of the health-related pathogens that we find in water systems. Again, in most cases, if you have a good chlorine residual in your water, you're not seeing a health problem. You know, you're handling these effectively. We learned that about a century ago. So that's good news. E. coli is an interesting bacteria in that we have a bunch of E. coli in our bodies. In fact, we rely upon it to survive. It's what helps us to digest our food. There just happens to be a strain of E. coli that if it gets in your body, it'll tear it apart. And so E. coli is a fairly common bacteria. Legionella is the same way. Legionella is all over the place, and there's 1 or 2 strains of Legionella that if it passes through your system and gets into one of your customer systems that has a hot water heater, then it can begin to multiply and you get outbreaks, things that you've seen like in the news recently from New York and other places where people die. Viruses, I mentioned, aren't actually living, but if they enter into your water system, they can pass and they can get entrained in the bacterial goo, the biofilm, and stay there long enough to eventually slough off and pass on to folks that drink the water. So even though they're not living, they can still cause a problem by simply being passed through the water system. And of course, we have other bacteria. Now, what's fascinating about bacteria is I mentioned we have 1 billion different bacteria types on the planet, it's estimated. Well, out of those billion, there are only 3 different structures, right? There's the rod shape that you see, the E. coli and Legionella and Pseudomonas and the Mycobacterium avian complex down there. Those are all rod shape. Then you have a small sphere shape, and then you have this curly shape right here, and that's it. So if you're looking under a microscope trying to determine the difference between these bacteria, you're not going to have much success. And so it's taken some fairly advanced techniques to be able to differentiate these different bacteria and be able to begin to understand what's going on. All right. And our regulations are based on short-term exposure and long-term exposure. Short-term being pathogens. If you have any presence of these pathogens in your water, it's a big deal. If for long-term exposure problems, you have annual averages. Okay, so you've got some in your water, that's fine, but let's not keep it in the water for very long, right? Let's clean it up, let's make it better. So it's more of a long-term exposure issue. And then here are some of the regulations and what their targets are. Again, these are all health-related, either pathogens, either short-term exposure problems, or they're long-term, like your disinfection byproduct rules. These or metals contamination, things that will accumulate and cause problems over time. All right, so we've talked a little bit about bacteria, give you a flavor of what it is and how it exists in our world, and we talked a little bit about some of the health problems that are associated with it, but that's really not the focus of what our meeting is today. Our focus is what does all the bacteria in our system do to our distribution system? How is it affecting us operationally? What problems is it causing? How does it cause those problems? All right, and so I think I've made the point that we really all have bacteria. There's no way around it. So anybody that comes to me and says, hey, we don't have bacteria in our system, well, you do. You just do. All right, so the sources of bacteria are going to be any sort of intrusion event. Low pressure, if you have leaks or valve problems, you can get bacteria in. If you have a filter that's not operating properly and you're getting breakthrough, you're seeding your system in that way. If you have finished storage vessels, maybe you have an uncovered storage vessel. They're not as common anymore, but or your vents are broken. Or even if the wind is blowing in bacteria that's on dust into your system is another way for bacteria to get into your system. So what ends up happening is you have a distribution system that has a lot going on. It's no longer just water with maybe some corrosion, lead or copper corrosion or something to that effect. You have biofilms forming, you have detachment, scale formation. It turns out that scale in a distribution system actually has a large amount of organic material built into it. Even if you have a hard calcium carbonate scale, like you might find in a cooling tower or something like that. it still has a high degree of organic content, somewhere between 5 and 20%. And that organic content, guess where it comes from? It doesn't come from inorganic compounds. It doesn't come from the pipe walls. It comes from the activity of the microbes, whether they're in your source water or in your source and just passing through treatment, or whether they're generated in your distribution system. That's where it comes from. And so everything that you see in this pipe is bound together through organic molecules. A lot of stuff going on, not easy to predict, and this is why every water system appears to be different, because every water system has a different balance of these different mechanisms going on. I just threw this slide in just to give a flavor for some of the things that microbes have a significant role in. And it's certainly not an exhaustive list, and it doesn't include a lot of things I can pick out right away here, but it does include things like corrosion and nitrification, water age and residence time. These are all microbiological issues. And so what's interesting about that is here in the States, and I guess anywhere, when we first address problems, we're addressing the problems that we can understand, and we're addressing them in the ways that we can understand how to address them. And what I mean is, for example, for the lead and copper rule, there are certain requirements for phosphates or orthophosphate use. Well, that works great because you can form a lead phosphate layer on a lead pipe and help protect it from getting lead into the water. But the problem with using phosphates is it's the same thing you'd buy in the hardware store to feed your tomatoes in your garden. It's designed to be, it's a primary nutrient, and it will make it possible for life to grow. So you're encouraging microbiological growth at the same time that you're trying to suppress maybe lead in your water, lead and copper or whatever. Same with ammonia. We add, first of all, wells have natural ammonia. That's fairly common. But also, if you're running a chloraminated system, you're adding ammonia into the system purposely to suppress the chlorine enough to make it all the way out to the ends of your lines. And so that, again, is another primary nutrient. So depending on how we're treating our system, we may be causing ourselves more problems than we would have had otherwise. Of course, we're solving problems at the same time, so I'm not saying it's bad. But I'm just saying it's important to recognize that just our normal practice of operations tends to encourage microbial growth. So residuals and disinfection byproducts. I want to get back to this idea that attached bacteria or biofilms, they really are factories. You have the bacteria will clump together and they'll protect themselves, and then they'll also feed themselves one way or another. And bacteria will eat anything. So if you're feeding it through the water system, through the water column, or whether it's taking its energy from the pipes itself by harvesting iron, it's basically producing, it's using the available energy that's around it to produce more bacteria and to produce byproducts. Some of those byproducts are disinfection byproduct precursors. Other byproducts would be additional bacteria, free-floating, causing your chlorine residuals to drop. Or you've got your residuals are working on that surface of the biofilm, trying to break it down, reacting with it, and it's just replacing the bacteria up to that surface. Or there's other organics and nutrients and particulates. You know, biofilms in general are interesting because as you get a mature biofilm, they can actually develop circulatory systems. They're almost like they're almost like animals. You get multiple bacteria that it's kind of like a fish tank, hydroponic fish tank in a growing farm, if you've ever seen this, where it just recycles from one organism to another. The same thing happens in biofilms. They're almost self-sustaining when they get together. And this is an example of one of those factories. And you can see, again, a bacteria showing up on the surface. It's growing, it's secreting its protective polysaccharides, and then eventually it will release bacteria back into the water, which will get killed by the residual that you have, but it will also wear that residual down. And so as you see over time, if you think of water age, a lot of water age is simply your residual reacting upon the bacteria that's being generated in these factories. And so likewise, what you see is a drop in residual as you go from the treatment plant out to the ends, and you see the disinfectant byproducts increasing. Corrosion is really governed by films. All kinds of corrosion are really governed by the kind of film that is on the surface of the metal, right? And those films can be formed in a couple of different ways. Uniform corrosion is a film. If you're familiar with aluminum, right, they use it to make sports cars. Aluminum is actually one of the more reactive metals on the planet, but it has a very effective film that's formed by uniform corrosion. As soon as oxygen hits it, it forms aluminum oxide, and it's basically inert at that point. So you have this inert film on top of a highly reactive metal, but the whole thing is inert for practical use. Well, the same thing can happen with metals. You can get a film that develops and it protects it. Well, any precipitation of compounds, metal, manganese, any other metal compounds, if they precipitate out of the water and they land on these films, they have chemical reactions and can result in different behaviors. Likewise, microbes will also form films, just kind of like we've been describing, these different films. And they also will have an effect on whatever kind of uniform corrosion is existing. This is a very complex problem, and there's really no good, accurate model or formula. Here's some of that tuberculation we've been talking about, and here's a few of the different chemical reactions that exist in the tuberculation. Here we see microbiologically induced corrosion, where we're actually pitting the metal because the bacteria is using the pure metal and oxidizing it. That's a source of energy for the bacteria, and it's making use of it to live, to grow, to power its factory. And as a result, we're drilling right through our metal, and we're producing the byproducts, which also cause a problem when it comes to flow in our system. Here's some examples of pits in pipe. You can see these little holes right here. It looks like somebody took a hole punch and just jabbed it right through. But those are microbiologically induced corrosion. Additionally, when you have when you have iron and manganese tuberculation, or any kind of particulates of iron and manganese, they're very good at sucking up the bad metals that you find in your system, lead, arsenic, and copper. And so those metals will very quickly attach themselves to the iron and manganese. So you may think, well, iron and manganese, well, it's a secondary contaminant. It's not a health problem. I'm not really concerned about it. It's a nuisance, but it's not a big deal. The problem is when you have a flush or a flow, high flow through a system that's got iron and manganese, you also have high surges of lead and arsenic or whatever else is somewhat normally fairly low, but it's been concentrated on these particles. So you can get very high concentrations depending on how you're sampling. The things we've been talking about, these films, these deposits, these bacteria, you've seen the tuberculation. That will all interfere with flow if it builds up too much. And if you have valves or you have meters, the valve operation will be hampered. You'll have to, you'll get out there to shut the water off and you won't be able to. You'll find that your meters slow down as they become accumulated with deposits. You may get 2, 3, 4% decrease in the amount of money you're able to charge for the water. People are getting free water from you because your meters are slow because of deposits and so forth. And you have increased flushing requirements. When you go to do your spring or fall flush, your system will take longer to clear up and turbidities will be higher. So this is just a refresher of the same kind of theme that we're talking about. Start off with simple bacteria, but you end up with an accumulation of problems that result in either water quality or operational problems. And so then the question is, what do we do about all of this? Well, for microbes, of course you might think, well, let's put in more disinfectant, right? Because disinfectant kills bacteria, and if bacteria is the root of all problems, then if we put more disinfectant in, we'll solve our problem. Of course, there's a downside. You're limited on how much you can put in, and there's taste and odor problems that come with using too much chlorine. And let's face it, the bacteria are really good at protecting themselves from chlorination. So instead, what we can do about it is we can simply just clean the system. If you have a tank or a filter or air scrubber, or something like that, you can just take them out of service. You can apply a cleaning chemistry Blue Earth Labs, what we do is we design and build these chemistries and sell them for the purpose of cleaning systems. So we have the ability to clean all of these different structures. Now, with piping, it's a little bit different, right? With pipes, you can't just take them out of service, and you really don't want to throw a bunch of chemistry in there, because who knows if you're going to get it all out with your valves causing you problems, right? You don't really want to put a lot of chemistry in there if you can avoid it. So we have a product called Claritas, which does a very effective job over time of cleaning out these systems, and it cleans it out by getting rid of the glue, essentially, that's holding all of these deposits together. I may have mentioned earlier that the deposits are interwoven with organic material, not necessarily living material, but organic carbon, hydrogen, organic molecules. And that's what Claritas will go after. And we'll see a little bit of that as we go through some of these slides. This is just an air stripper. You can see the media in an air stripping tower before and after cleaning. You can see that if you are able to clean it chemically, you're able to get down into all the crevices, and you're able to get the bacteria out of your system, get those factories, shut them down, and you're able to pass through your water quality. Your good water quality from your plant can pass all the way through your distribution system. Here's filter bays, same principle. We've got befores at the top and afters at the bottom. This is just a simple spray application, and it dissolves these deposits and breaks them down and gets rid of them. Filter media, we have a very high surface area on filter media. That's why we use it. But when it gets dirty, when there's bacteria attached, remember 99% of your bacteria is attached to the walls of your water system. When they're attached to the media, they become a problem. They will add precursors for disinfection byproducts into your water system. They will allow bacteria to slough off and make it through. They'll interfere with the operation of the filter. And so if you're able to clean the filter media by simply applying some cleaning chemistry in one day and bring your filter back up to new, then you're able to operate your filter the way it was intended to. And you'll have better water quality, and you'll see those effects all the way through your system. So you improve operation performance, improve water quality, as well as reduce the amount of maintenance you have to do. You won't have to change out your filter media if you can clean it yearly. And you'll be able to have like new filter performance if you clean it on a regular basis. And this is a slide. You'll see a couple of these slides that look similar. And what I'm trying to convey here is if you have a dirty system, you have water quality issues. If you have a clean system, you're able to pass that good quality water all the way through. Tanks are the same way. Not quite as much surface area, but the water spends a lot more time in a tank in contact with that surface. So the impacts are also significant. Here's 3 tanks that were dirty on the top, and then 3 at the bottom that were used. I think we used Top Ultra to clean these tanks. We had one bad tank that we took the time to actually measure the residual drop in this clear well before we treated it and then after we treated it. And so for the 22 hours before we treated it, we lost 94% of the free chlorine. That's a large drop for a clear well. Okay, so this is an extreme example, but it's here to show you that what can happen if you let your system go. So we had a 94% drop just in contact with the walls of the clear well. Then after cleaning it, we lost 14% in 24 hours. And then this is just a clear jar, a glass jar, that we also used as a control to find out how much would drop in a clean situation. And so we see about the same. And likewise, if you'll see the clear well, after cleaning, we're able to maintain a much larger residual out of it and then into the tap. So you see, this is the after, this is before. Much larger drop across from the plant, the clear well, to the tap. Beforehand, after cleaning, we're able to pass that good water quality all the way through to the customer. Distribution systems, we talked about how all of these, what makes up all of this circulation, all of this gunk. But now we need to talk about how to get rid of it. And it's not an easy thing to do. If you're going to pig it, that's fine. It'll move the large, massive material, but it's not going to be able to clean the bacteria that's off on the sides of the wall. It's not going to clean it in such a way that's going to prevent it from causing you water quality problems. It'll improve it, no question. So Claritas, I mentioned, it's an advanced hypochlorite derivatives, right? So it's based on kind of a bleach chemistry, so it's something that you're somewhat familiar with, but it's been modified to attack the organics that hold all of this stuff together. So you really don't need very much of it because it attacks the components that hold the deposits together. So we might dose, on average, just a few parts per billion of active ingredient into your system, and it works quite well. And how fast it works is determined entirely by the dosage that you use. And so here's an example of a system where they started off, the black is the plant, the blue is at the distribution system. Here's where we started injecting Claritos. You can see they made several improvements beforehand in the plant, trying to fix the issues that they were having there. And they wanted to improve it in the distribution system, so they added Claritos. And you could see, as they were able to go along, that the free chlorine that they were pumping out of the plant was able to be passed all the way through to the distribution system after they were able to clean their distribution system. And as a result, I mentioned that chlorine and disinfection byproducts are related. In this case, you have THMs dropped a fair amount afterwards. The HAA5s dropped significantly afterwards. And this is an indication that the precursors for the THMs were probably from the source water, or they're from something prior to the distribution system. Whereas in this particular case, remember every case is different, but in this particular case, it looks like the precursors for the HAA5s were probably heavily generated in the distribution system. And that's not always the case, but it was in this one. When you take the time to clean your distribution system or any other component of your system, you receive a variety of benefits, just like what we've been talking about. You know, you can improve, just by addressing this one issue, you can improve your corrosion rates, you can extend the life of your infrastructure, you can improve your flow rates over time, certainly reduce customer complaints, and improve residuals and reduce disinfection byproducts. You're like, so now that we're understanding where a lot of these problems are coming from, and that they're coming from the microbes, and if you can work on those and understand them better, you can more effectively improve the operation of your facility, and as a result reduce the amount of money that you have to spend all over your system. All right, so we're drawing to the end of this talk, and just wanted to reemphasize the importance of microbes, not only in water systems, but in everything that we do, right? And nearly all of the water problems that we have can be traced back to microbes, whether they're the original source of the problem or they simply exacerbate the problem. So the goal here is to keep the system clean. Okay, thank you very much.